Hello guys, welcome to this new video, and now we are going to go through question 9, the last question in the May 2022 time zone 2 paper 2. So we are told that we have a beam of electrons of energy 440 mega electron volts and they're incident on oxygen nuclei, and we're given the variation of scattering angle and the relative intensity of the scattered electrons. So what is going on in this experiment is like we have some oxygen nuclei, and we project some electrons onto them in the form of an electron beam, and then we have, like this is the middle, and we have some observer moving at different angles to our position of incidence. So this is the angle theta, and we're moving this machine up and down, which measures the intensity. And what we notice is that when we change this angle, at a specific angle, we have a minimum of intensity. And this first question wants us to identify the property of electrons demonstrated by this experiment. And well, if we see this graph, this is very similar to that of a diffraction pattern, which looks something like this, where we also had a minimum intensity at a specific angle. And we have that here as well. So what this is suggesting is that electrons also behave like waves, because only waves can be diffracted through the gaps in between the oxygen nuclei, so to say. Of electrons. Because if there would be no diffraction, the only reason electrons would scatter a little bit is because of the Coulomb force, so the electric repulsion between the electrons and the outer electrons of the oxygen nuclei. That is why this graph looks a little bit different. But if there would be no diffraction, we would only observe that pattern. It would probably look something like this. But it clearly doesn't look like that, and that's because the electrons in fact do diffract, and so they form this diffraction pattern, where we know from previous topic C that when a wave diffracts like this, it will form minimums of very small intensity, or in this case not zero intensity, but close to zero. At least it's a minimum. And then in the next part, we need to show that the energy of the electron beam is that many joules. Well, we're given it in electron volts, so we just need to know how to convert electron volts to joules. And well, the way to do that is, first of all, we need it in electron volts, not in mega electron volts. And then once we have it in electron volts, we just multiply it by 1.6 times 10 to the minus 19. And that will give us 7 times 10 to the minus 11 joules. So it's just important to remember how to convert from joules to electron volts and from electron volts to joules. These types of questions, we often are tested on this. And then we know that the de Broglie wavelength for an electron is given by this formula. And we need to show that the diameter of an oxygen nucleus is about 4 femtometers. So, well, firstly, we can calculate the de Broglie wavelength of the electron. So it's going to be hc over E. We know h is just Planck's constant, so 6.64 times 10 to the minus 34 times the speed of light, 3 times 10 to the 8, and is divided by the energy of the beam, which we have just calculated, 7 times 10 to the minus 11, yes. So for this we get 2.8 times 10 to the minus 15 meters. And well, we know that this is a diffraction pattern, and here we have a minimum, and we know that this angle over here, which is, if we look very closely, is going to be 46 degrees. This angle is equal to, so the sine of this angle is just the wavelength divided by the diameter of the atoms we are shining the electrons at. So we can rearrange for the diameter, and so that will just be lambda divided by the sine of this minimum angle. So 2.8 divided by sine 46. So this will give 3.9 times 10 to the minus 15 meters. And then the final question in this paper, we need to estimate, using this previous result, the volume of a tin nucleus, and we need to state our answer to an appropriate number of significant figures. So, well, the fact that we need to use here is what we should remember, is that the density of nuclei is approximately constant. Or I mean, in ideal conditions, it's constant. Density of nuclei is constant. So what this means is that the mass of the oxygen divided by the volume of the oxygen atom is equal to the mass of the tin atom divided by the volume of the tin atom, as density is just mass over volume. And well, we know the mass number is, we can use that as the mass. So the for oxygen is 16, as we used oxygen 16 in this example. And we know that the volume of this can be calculated with 4 pi r squared, as that's the volume of a sphere. I mean 4 pi r cubed, sorry. 4 pi r cubed. And then the mass of the tin atom is 118. Again, that's the mass of all the protons and the neutrons inside the nucleus. And then we divide it by the volume of the tin, which is what we need to find. So we can simply rearrange for this Vsn, the volume of the tin, and so that will be 118 times 4. Well, I messed it up again, so it's 4 over 3 pi r cubed. I confused it with the surface area, which is 4 pi r squared. So the volume is 4 over 3 pi r cubed. So 118 times 4 over 3 times pi times this radius we found in the previous part. So that will just be the half of what we found over here. So yeah, I forgot to mention, but 1 femtometer, so this is approximately 4 femtometers. 1 femtometer is 1 times 10 to the minus 15 meters. So this is the diameter. So here we would have to plug in d over 2, and then we divide it by, of course we cube it, and then we divide it by 16. And so from this we will get that the volume is 2.3 times 10 to the minus 43 meters cubed. So really small. And well, this is already to an approximate number of appropriate number of significant figures, as our diameter or our radius was to 2 significant figures. That's the only real value we used here, so our final answer will also be in 2 sig figs. And so this was the end of the May 22 Time Zone 2 Paper 2. I hope these videos were helpful, and see you in the next video.